Good day, this is the Professor drwillphd, PhD. Today is Tuesday, October 25th, 2022. It is 1:40 and 17 seconds. Dinosaur killing asteroid triggered global tsunami that soured seafloor, thousands of miles from impact site. Date October 4th, 2022. Source, University of Michigan. The miles-wide asteroid that struck Earth 66 million years ago wiped out nearly all the dinosaurs and roughly three-quarters of the planet's plant and animal species. It also triggered a monstrous tsunami with mile-high waves that soured the ocean floor thousands of miles from the impact site on Mexico's Yucatan Peninsula, according to the researchers. In addition, researchers reviewed the geological record at more than 100 sites worldwide and found evidence that supports their model's predictions about the tsunami's path and power. And this tsunami was strong enough to disturb and erode sediments and ocean basins halfway around the globe, leaving either a gap in the sedimentary records or a jumble of older sediments. The review of the geological record focused on boundary sections, marine sediments deposited just before or just after the asteroid impact, and the subsequent KPG mass extinction, which closed the Cretaceous period. The distribution of the erosion and hiatus that was observed in the uppermost Cretaceous marine sediments are consistent with the model results, which gives more confidence in the model predictions. The study authors calculated the initial energy in the impact tsunami was up to 30,000 times larger than the energy in the December 2004 Indian Ocean earthquake tsunami, which killed more than 230,000 people and is one of the largest tsunamis in the modern record. The team's simulations show that the impact tsunami radiated mainly to the east and northeast into the North Atlantic Ocean and to the southwest to the Central American Seaway, which used to separate North America and South America into the South Pacific Ocean. And in those basins and some adjacent areas, underwater current speeds likely exceeded 20 centimeters per second, 0.4 miles per hour, of velocity that is strong enough to erode fine-grained sediments on the seafloor. In contrast, the South Atlantic, the North Pacific, the Indian Ocean, and the region that is today the Mediterranean were largely shielded from the strongest effects of the tsunami, according to the team simulation. In those places, the model current speeds were likely less than the 20 centimeters a second threshold. And for the review of the geological record, researchers analyzed published records of 165 marine boundary sections and was able to obtain usable information from 120 of them. Most of the sediments came from cores collected during the Scientific Ocean drilling projects. The North Atlantic and South Pacific had the fewest sites with complete, uninterrupted KPG boundary sediments. In contrast, the largest number of complete KPG boundary sections were found in the South Atlantic, the North Pacific, the Indian Ocean, and the Mediterranean. Researchers found corroboration in the geological record for the predicted areas of maximal impact in the open ocean. The geological evidence definitely strengthens the paper. Of special significance, according to the researchers, are outcrops of the KPG boundary on the eastern shores of New Zealand's North and South Islands, which are more than 12,000 kilometers, 7,500 miles from the Yucatan impact site. The heavily disturbed and incomplete New Zealand sediments, called listostromol deposits, were originally thought to be the result of local tectonic activity. But given the age of the deposits and the location directly in the modeled pathway of the Chicxulub impact tsunami, the research team suspects a different origin. Researchers feel these deposits are recording the effects of the impact tsunami, and this is perhaps the most telling confirmation of the global significance of this event. The modeling portion of the study used a two-stage strategy. First, a large computer program called a hydrocode simulated the chaotic first 10 minutes of the event, which included the impact, crater formation, and initiation of the tsunami. And based on the findings of previous studies, the researchers modeled an asteroid that was 14 kilometers, 8.7 miles in diameter, moving at 12 kilometers per second, 27,000 miles an hour. Its dark granitic crust, overlain by thick sediments and shallow ocean waters, blasting a roughly 100-kilometer wide, 62-mile wide crater and ejecting dense clouds of soot and dust into the atmosphere. By 2.5 minutes after the asteroid struck, a curtain of ejected material pushed a wall of water outward from the impact site, briefly forming a 4.5 kilometer high, 2.8 mile high wave that subsided as the ejecta fell back to Earth. And 10 minutes after, the projectile hit the Yucatan at 220 kilometers, 137 miles from the point of impact. A 1.5 kilometer high, 0.93 mile high tsunami wave, ring-shaped outward propagating, began sweeping across the ocean in all directions, according to the research simulation. At the 10-minute mark, the results of researchers' hydrocode simulations were entered into two tsunami propagation models, MOM6 and MOST, to track the giant waves across the ocean. MOM6 has been used to model tsunamis in the deep ocean, and research uses the MOST model operationally for tsunami forecasts at the tsunami warning centers. The big results here is that two global models with differing formulations gave almost identical results, and the geological data on complete and incomplete sections are consistent with those results. According to the team simulation, 1 hour after impact, the tsunami had spread outside the Gulf of Mexico and into the North Atlantic. Then later, 4 hours after impact, the waves had passed through the Central American Seaway and into the Pacific. Then 4 hours after impact, the waves have crossed most of the Pacific from the east and most of the Atlantic from the west and entered the Indian Ocean from both sides. And by 48 hours after impact, significant tsunami waves had reached most of the world's coastlines. And for the current study, the researchers did not attempt to estimate the extent of coastal flooding caused by the tsunami. However, their models indicate that open ocean wave heights in the Gulf of Mexico would have exceeded 100 meters, 328 feet, with wave heights of more than 10 meters, 32.8 feet, as the tsunami approached North Atlantic, coastal regions, and parts of South America's Pacific coast. As the tsunami neared the shorelines and encountered shallow bottom waters, wave heights would have increased dramatically through a process called shoaling. Current speeds would have exceeded the 20 centimeters per second threshold for most coastal areas worldwide. Depending on the geometries of the coast and the advancing waves, most coastal regions will be inundated and eroded to some extent. Any historically documented tsunamis pale in comparison with such global impact. Good day, this is the Professor of Environmental Science, Ancient History, and Computer Mathematics. This video was created for educational purposes only. Hope you enjoy listening. Until next time, have a great day.